At last, we want to look at the beginning of the evaluation basics and how we figure out whether any given classifier that we construct, be it a concept classifier, be it a regression classifier, can be assessed with regards to whether it effectively makes a prediction. It is not as simple as just optimizing a classifier or fitting the classifier or the model function to the data, because we then don't know, if we choose all of the data, whether it will work in practice. If we want to figure out whether a given model function has a chance of working in practice, what we need to do is to look at, hold back some cases for testing. So we need to estimate how well that model function will work. And this estimation, I want to now show you how it's done. This is fundamentally a probabilistic estimation that we are doing here. But probability comes into play to some extent now, but not as much as one might think. It's still technique mostly. So some introductory illustrations here. This is our set of objects. We have some texts here that we want to classify. Let them be emails. We want to classify them, whether they are ham or spam. And we ask a human to do that for us. The human is now our ideal target function, which gives us an idea which objects belong to the target concept, spam, and which objects belong to not spam or ham. We choose two features. For example, the number of spelling errors in the emails and the number of URLs found in the emails. Whether or not these are good features is another discussion, but for simplicity, let's just choose two features. This is our model function. This creates the features for our model function, and counting the number of spelling errors and counting the number of URLs in an email is basically then our model formation function. So we map all the real-world emailed objects into this two-dimensional space. And what we see is, given these two features, by construction also, that there can be emails which have the same number of spelling errors and the same number of URLs, albeit they are two different emails. And we may see that there are two examples now, X7 and X8, which look different but are mapped to the same feature vector. And here again, X1 and X3 belongs to O1 and O3, also two different emails mapped to the same feature vector. And here again, 3 emails mapped to the same feature vector. So we choose this to make it a little bit extreme that this happens. This cannot be avoided. This is why we call this set of feature vectors that we have a multiset. So we always have the situation that objects are mapped to the same feature vector. This in itself means that there's some more weight on some places of this two-dimensional space here than there's on other places, simply by the fact that given the chosen features, more objects land here than here. And you can see now that there's a distribution of objects over the different possible spaces here. It's a discrete space because we choose the number of spelling errors. It can only 0, 1, 2, 3, 4, 5, 6, 7. It cannot be something in between. Same with URLs. So it's a discrete space, but in every slot here, we have a certain different number of objects that fall into that slot. So there's a distribution here, and you see that there's some probability already involved. And again, even if you choose real valued features, so that can actually have real values, they will not distribute evenly across that space, which makes this then a continuous probability situation. Our classifier, our linear classifier, or model function that we chose here, could be a neural network like this, a neuron here, or it could be anything that we have seen before, then makes a decision now based on the parameters that we chose. And that decision may look like this. For the objects 02, 04, 05, and 06, it decides they are ham. And for the objects 01, 03, 07, and 08, or rather, in both cases, for their respective feature vectors, the model function decides that they are spam. Starting from this situation, we see that we can compute already an error. The model function made errors. Emails that were classified by our ideal target function, the human judge, as ham are actually called spam. As spam are actually called ham by the model function, and vice versa. So the objects x6 and x8 are falsely classified. This is the error that the model function makes, and we can quantify that error now given this data that we have here. The quantification of that error, given all possible examples that we have in our mapping from O to the multiset X, is the number of examples that are falsely classified. So the size of the set of examples for which the model function computes the false class. And here we can estimate it with these 8 examples as 2/8 or 0.25. It is important here that this error function, and this is also why it gets the star, to mark it as something as the true error function. This error function here is over the entire set of objects that is there, that have been mapped to our feature space. So this is the feature space, this is the multiset of features, and if this is the entire set of objects in the real world, then this is the true error of our model function. It is crucial to understand that this is the true error, but we will never be able to find the true error in reality. Because usually we don't just have 8 emails. There are an untold number of emails in the world, and only very few of them have actually been used for spam classification, or rather have actually been seen by that particular human. So in reality, or rather in practice, not in theory, in practice, we are just looking at a couple of examples and then computing an error based on that. But this is just an approximation of this error function. So what we see here, if compared to that, this is an approximation given the examples that we have seen. But this is the actual truth that we would like to estimate. Is that clear, the difference between the true error and the estimated error? Okay, good. We can look at the same situation probabilistically again. So, for some reason, 3 different objects are mapped to this very same feature vector. They have 4 speller errors, but 0 URLs each. They are even the very same objects, interestingly, just by the looks of it. The same email can be sent multiple times, no problem. They are different objects because they have a different timestamp in the real world, but they are basically the same and therefore truthfully or correctly mapped to the same dot in the feature space. But if it happens that this particular email gets sent multiple times, could be an automatic email and it happens to have 4 errors. If it happens that such emails like this are sent multiple times, that makes encountering them more likely compared to this email, for example, which just occurred once. 3 mistakes and 2 URLs. So these emails are more likely than that email. Same with these here. These are more likely than that. And here, oh no, these are not more likely than that. Those two are equally likely. However, here we have a different situation, that the likelihood of seeing this email being classified as spam versus seeing this email being classified as ham is different. So if we want to use, if we want to look at the whole situation from a probabilistic standpoint, then the true the base error, basically the base what's it called? The error of the base optimal classifier is basically the probability of the joint event of observing an email X of the class C multiplied by the indicator function, whether or not the model function that we are evaluating actually misclassifies that email. And the indicator function just returns 0 if it classifies the email correctly and 1 otherwise. So we are just summing the probability mass, all the probabilities of all the misclassifications. And that gives us the joint probability of the error. And this can be computed as well. So we have a likelihood of seeing this email 3/8 of the time, 1/8 for this, 2/8 for this, 1/8 for this, and 1/8 for this. And this is then the result of the indicator function, and we get the same result. These are two different but equivalent views on the same situation. What is the actual error of our model function? In both cases, we mark this particular function with a star, simply because it gives us it is supposed to denote the true error, the actual error of the model function in the real world, if we had access to the ideal classifier. If the human has seen all emails in the world. It is not realistic, I know that, but it is crucial that you understand that this is the theoretical construct of the true error. In practice, we try to estimate this through evaluation. So this is the whole thing which comes now in the rest of the slides in a nutshell. Now we get started. Perhaps what we see here is there's another thing. So this is the true error, and another question that we should ask is, can we improve over the situation? Can we choose a different model function that has a smaller true error? And yes, we can. We can fix errors in our data. So if we have, for example, more data, let's put it the other way around. This is actually spam, it has been misclassified, but if we happen to have more examples that fall into this bin of this email, then the model function might just be tilted a little bit so that these emails are correctly classified. So fixing this error means probably collecting more data so that this is better represented compared to that, because these vectors here are quite similar, more or less, in terms of at least their first dimension. Okay? These overrepresent the ham classification compared to the very similar vector of the spam classification. So we need more emails like this in order to tilt the model function the other way, and thereby have a different model function that has a smaller true error. These errors, however, they cannot be as easily fixed. This is label noise. The expert has called this email spam and this email ham. here we would, by choosing a different model function, namely a different parameterization of my model function, we can't change anything because the feature vectors are still the same. We can't draw a line between two objects which are on the exact same dot in the feature space. So the only thing that we can do is go back to the drawing board and find different features which help us differentiate these two emails. This is what is called label noise, and it also cannot be avoided. We have talked about this a little bit in the beginning when looking at the chessboard example. So a grandmaster of chess looks at the board and the entire situation, takes in everything, the entire situation of the chessboard and makes a decision. But we have just chosen to count the number of white pawns, the number of black pawns, the number of pawns which can be attacked in the next move, and so on and so forth. These are just a couple of small examples of representing a chessboard, whereas the grandmaster of chess looks at the board and sees everything at the same time. We cannot represent a real-world object perfectly in the computer. We always have a discrete representation, regardless of how many features we choose. If it's just 2 or 200, 2000, 2 million, doesn't matter. We will never have the finesse of the real world, unless, of course, in the real world the object is just so discrete. So, therefore, regardless of how many features we choose, we will always have to live with the slight probability that there may be such situations where two different objects with different classes are mapped to the same point in the feature space. It happens. There is even another source of errors that we have not talked about and that is not shown here, but which can also lead of this situation. Can you imagine which it is? If we go back again a little and look at this. Maybe add a little bit closer. Look at this. Yeah?
Maybe the expert did a mistake?
Yes. Human error, for example. So you could say now, if a human gives us data that is contradictory, like this, calling similar emails ham or spam. These are not similar emails, but it could just be that the human makes an error here and calls one spam and one ham. Could be. This is an honest mistake. It happens in the real world. People don't pay attention in the same way or come to the same conclusions at the same time all the way. It could be that still we have not modeled the situation correctly, because on one day the same email may be spam when on another day it is not. Could be. However, it can just be that our measurement device of the real world, the human, is just faulty. If we make observations that are not human-based, but observations from some other measurement device, for example, like taking the temperature, measuring the temperature using a thermometer. Every thermometer makes a mistake. It gives you a value, but this value will be slightly distributed, randomly distributed across the true temperature that you are measuring. Because every measurement device makes a mistake. It cannot be perfectly accurate. And this random error, this cannot be removed. Or you can come up with a more elaborate measurement device. Use one thermometer and use another thermometer and make two measurements and take the average. Or you can have a third. You can have more measurements. You can ask a human. You can do all things. But in essence, this could all be part of the ideal target function. This is the ideal target function. However you make your labels is up to you. And of course, it is part of machine learning, part of modeling, or part of transferring the real world into a model world, of coming up with good labels and doing double checking and trying to mitigate, account for human error and all these kinds of things. This is all part of the process of labeling. So this is all integrated into this function. It is not a single human making a one-time shot, but it could be 20 humans each looking over, whereas 2 random humans always look over the same email to figure out whether they are coming up to different conclusions. Then when they come to different conclusions, they start discussing which is which, and they may still make errors. Every measurement device that makes observations in the real world makes errors. Also cannot be avoided. The goal of machine learning is primarily not to fix the real world. The goal of machine learning is to come up with a model function y that approximate this gamma as closely as possible, even if it's erroneous, even if it makes random mistakes. So the model function that we choose should as closely as possible approximate gamma and minimize the error. And then there's some irreducible error that cannot be gotten rid of at all. And this is then the label noise of gamma. All right, so some definitions. We have seen now in the illustrations this error function here, and this will now be defined. We call it the true misclassification rate. In German der wahre Missklassifikationsanteil oder die wahre Missklassifikationsquote. Nicht Rate. Because in German there's a difference between Rate as a frequency over time, as something appearing more than once over time, versus just the ratio, the portion of something. It's a common mistake to be made for Germans. So, the true misclassification rate, or the true error of a classifier y, is defined as follows. We are given a finite set of objects and a feature space that is due to a model formation function alpha, which maps the objects to that feature space. And we are also given a set of classes and a model function which maps from the feature space to the classes. And we are given the ideal target function, which maps the objects to the classes, the ideal classifier, which is to be approximated by y. So, we are now given a multiset of feature vectors, which have been computed by transferring all objects to their feature value, to their feature vectors. This is our multiset. And for each of these feature vectors, we know its class, which is computed by the ideal target function. So again, since all objects in the real world can usually, even if finite, not be enumerated, we usually have also no real access to that x. But for the sake of argument, let's consider these objects to exist. And they do exist in a sense. The objects look like this. We have duplicate emails, which occur in the real world, and many of them. And we have the feature space in which they are mapped. For example, our 2 features that we saw before. The objects are mapped by the model formation function, and these are the feature vectors that we actually get in our feature, in our multiset X. So all the objects that we encounter are mapped by alpha, and they are also duplicates somehow here. The ideal classifier maps these objects to their class. And the model function maps the feature vectors to their class. And what we see here is situations where the model function makes errors. If the model function makes an error like this, where an object is mapped to the wrong class, although it is supposed to be mapped to the right class, we can fix this error by fixing the model function. If an error like this occurs, where an object which is mapped to the same point in the feature space is mapped to different classes in the real world, this cannot be fixed in the model world of the model function. So, in this situation, we call the true misclassification rate of y, which is denoted by error star of y, we define this as follows. It is simply the number of feature vectors which are misclassified divided by the total number of feature vectors. Same, we could translate this in the same way in the using the object notation. The problems that we have is we do not know the entire population, therefore we do not know all feature vectors. And even if we knew all possible feature vectors of the entire population, we don't have access to the ideal target function, and therefore cannot know all of their classes. What we can do, however, is estimate this error based on a set of examples D. And this estimation is what we call evaluation of y. And the estimation that we want to do should give us perhaps upper bounds and lower bounds of this error, so that we can make an educated decision whether a given model function, based on the data it has been trained on, is actually good or not. All of this is also written here. And now, for comparison, the probabilistic view. We see here, we want to define here the probabilistic foundation of the true misclassification rate. And if you remember your stochastics lecture, you know what a sample space is. It is the outcome, the set of outcomes of a random experiment, omega. And this, in our definition here, corresponds to the real-world objects. So the real-world objects are the outcome of a random process. And we have a probability measure which is defined over the power set of these outcomes, of the power set of omega, which is our event space, Ereignisraum. We define X to be the feature space with a finite number of elements, and C is a set of classes, and Y is our model function, which maps the feature space to the classes, the classifier. And here, now we introduce and consider two types of random variables. Notice the difference in notation again. Here's the upright X, fat X, which maps the outcomes, so the objects, to the feature space. And the random variable C, again, different notation, no serif font, which maps omega to the classes. Again, let's look at this within an illustration. We have again our real-world objects here. And we have our model formation function, which maps them to the feature space. And the ideal target function, which maps the objects to their classes. Now translate this to the probabilistic view. The sample space, omega, is the set of all objects. It is the outcomes of some random process which generates emails. So from somewhere the emails must come. We don't know how they come into the world, so it could as well be a random process. The random variable C is a mapping. Random variables are always functions which map objects, events, basically, to their classes in this case. Outcomes to their classes. And we have another random variable which maps outcomes to the feature space, to a place in the feature space. And based on this formulation, we can now compute the probability or estimate the probability of certain events. Namely, the event that, or the probability of the random variable X taking on the feature vector x, the value of the feature vector x. So the probability of mapping some object to this place. And this can also be written shorthand here with the lowercase p. This is actually a different kind of function. So this is an event, if you remember. The event of this mapping having taken place. This again maps the actual number to a probability. So there's a different pre-image here for these two functions. But for all practical purposes, this is equivalent here. Or we can look at the event that we observe a certain class. We can ask, what is the probability of observing C2? And we see we observe it a couple of times compared to C1. We can compute that. We can compute the probability of observing X. So this X, for example, 2 out of 8. And we can compute the probability of joint events as well. So this modeling classes and feature vectors as a joint probability distribution. And we can say the event is like this. The probability of the random variable x taking the value x and the random variable c taking the value c. So the probability of observing a feature vector x and a class c. The comma stands for and. Different notation. We can, of course, also look at conditional probabilities. For example, the probability of observing a feature vector x given a class. These are two different things, although for the later there are some equivalence between them. We will look at them very closely, don't worry. We can now continue the definition of the probabilistic foundation, and given the joint probability of feature vector and class, which is basically the same as writing this, the probability of the joint event to get the feature vectors and the respective object belongs to the class C. With this probability, the true misclassification rate can be also expressed like this. It is basically the sum over all probabilities of misclassifications of any given x, combination of x and c. This indicator function just makes these factors here 0 or 1, given whether the model function makes a correct classification or a wrong classification. If the model function classifies a feature vector correctly, this function evaluates to 0 as per this notation here, and therefore eliminates this factor out of this part of the sum. If the model function makes an error, we accumulate that probability to the total sum. And that's all. It's just a huge sum that we are computing here. And this is then the probabilistic way of looking at the true misclassification rate. Why are we looking at this so much? It's not, I don't want to torture you. So that's not the point here. The point here is to make it clear to you that the foundation of evaluation and the foundation of machine learning in essence as well is probabilistic in nature. You ought to know this at least in order to, and then if you apply a certain technology, that there are some probabilistic foundations here, and especially some errors that you cannot get below. So, again, just like before, we do not know P or the joint probability distribution because we don't have all data. In order to compute the joint probabilities, we need all data, all objects, all their representations, all the probabilities with which objects are mapped to certain places in the feature space, and so on and so forth. And the ideal target function as well. Nevertheless, we can make estimations, and this is can be done based on naive Bayes assumption. So, to close the lecture, I want to give you a couple of illustrations, and perhaps, no, I think I will leave it at that. It's enough for now. Here, the probabilities will be illustrated a little bit, but we will start here again next time. All right.